Yeah, so it's a rather ambitious title, Paths to Human Level AI, and I'm afraid I'm not going to be able to quite give you the secret of how to do it and make your first trillion yet, but I'm going to give you some of my thoughts on this subject. And it's really because artificial intelligence as a field has sort of become very interesting again lately, largely due to the progress that's been made in subfields like particularly machine learning and also computer vision. And so I've been thinking a lot lately about this question of how might we one day achieve human-level artificial intelligence. And I've been reflecting on some of the work that I've done over the last 10 or 15 years and thinking how it might sort of blend with some of the advances in machine learning that have been coming out recently. So that's really what I'm going to be talking about today. So that's the overview. We'll just get started, okay? Okay, so this is the gratuitous picture from the gratuitous still from Ex Machina, because, as was mentioned, I was somewhat involved with the film. It has no bearing on the talk whatsoever, but you know, there's a picture there. So what I'm interested in really is well, we really have no idea quite how we're going to get to human-level artificial intelligence. And where we are now, there's a kind of state-of-the-art where we are now, and there are all kinds of different ways that we might think perhaps of moving towards human-level artificial intelligence. We might, so you know, people were interested in a symbolic classical AI approach many decades ago. Nowadays, deep learning and machine learning seems to be the kind of where the action is, but maybe brain-inspired computing or some kind of quantum stuff. Structured gel is actually what the guy in Ex Machina says, that the blue brain that he holds out, Ava's brain, is made of structured gel. So there's no such thing as structured gel except in the film. But basically, what a message I'm trying to convey here is that we really don't know how we're going to get to human-level AI. But what I'm interested in is taking these little sort of shoots, if you were, and seeing where they might go next in this sort of direction. So particularly machine learning. And so I'm often giving talks about artificial intelligence and the future of AI, and I frequently have to make this very, very important point to distinguish between specialist AI technology of the sort that is around today and general AI of the sort that we're sort of imagining, that we're aiming for, that we see in science fiction films. So today's sort of success stories, when we think about things like self-driving cars or personal assistants like Siri and so on, and these kinds of technologies that are undoubtedly going to have a dramatic social and economic impact over the next 10 years. But of course, they're not what we see in science fiction films. They're not human-level artificial intelligence. They're not general AI. And the point is that general intelligence is capable of achieving an enormous variety of tasks, not just one particular specialist task, and of learning completely new tasks, and even of inventing completely new kinds of tasks. So this is what marks the human out from any kind of AI that's around at the moment, is the fact that we have this kind of general capacity. And I often use the example of Garry Kasparov, who of course played very good chess, no doubt still plays very good chess, but was defeated by Deep Blue in 1997 when he was the world chess champion. But of course, the amazing thing about Garry Kasparov is not really just that he can play great chess, because Deep Blue can play great chess, but it's that he's an animal who is capable, who has a brain that's capable of doing a whole variety of other things, of conducting a conversation, of making breakfast, of driving a car, just a huge variety of things, and learning a huge variety of different things, and can still play really good chess, which is something that, of course, Deep Blue couldn't do. Deep Blue couldn't even play noughts and crosses or drafts or anything like that. So human-level intelligence, human-level AI demands general intelligence, and there are two things that I think are some of the most important obstacles between where we are now, the state of the art, and achieving human-level AI. And these two obstacles that I'm often citing are common sense and creativity. So what I mean by common sense is the ability to anticipate and predict the consequences of actions and events in the everyday world. And by the consequences of these events, I mean both the physical consequences and the social consequences. So for example, if I were to suddenly take hold of the leg of this three-legged table and were to sort of lift it up like that, you can all imagine straight away, although you've never seen this done, presumably, and you probably never even imagined this before, but you can straight away have a pretty good idea in your head of what's going to happen. This, my laptop is going to kind of start flying over there. This will slide off. The wires will get all entangled. It'll make a big crashing noise. It'll probably tumble down these steps a little bit. You'll all be shocked. You might have to call the gendarmerie, to have me carted off, because this will be very peculiar. So you understand straight away that it's a completely novel and very strange situation. We all immediately understand both the physical consequences and the kind of social consequences of this strange action. So this kind of common sense ability to predict these consequences of everyday actions is not something that we know how to endow a computer or a robot with yet. And the other one is creativity, which I've characterized here as the ceaseless tendency to try out new things and to experiment and to be playful. And the kind of creativity, there is not something that is confined to the Picassos and Mozarts and Einsteins of the world, but something that every child exhibits when they muck around and learn how to do something new, when they build something out of Lego or do a weird drawing. Anything like that is the kind of creativity that's in question. And I think those two things, common sense and creativity, are at the basis of intelligence and what we don't really know how to do yet. Okay, so now I'm going to talk, so now there are like two bits to my talk. I'm going to talk quite a lot about the current state of the art in machine learning and where that might go. And then I'm also going to talk a little bit about the work that I did in the past on cognitive architectures and how these two things can be joined together. And the main thing I'm interested in is the idea of a predictive model and what the state of the art is in building predictive models with machine learning, and then how we can incorporate them into more complex cognitive architectures. So that's really what I want to talk about. But first of all, I want to set it in a sort of very general context. So I think that we can, let's have a little show of hands. So how many people here are familiar with the idea of reinforcement learning? Okay, excellent. So I feel in that case I can take a little bit for granted for what we mean by reinforcement learning. So this is a kind of general reinforcement learning architecture. Now you may be familiar with the diagram that you see in Rich Sutton's book from back in the 90s, where we have an agent, and the agent performs actions which influence the environment, and then from the environment we get a modification to the state, we get state updates, and then we get a certain kind of reward. And the task of reinforcement learning is to learn a policy for action that will maximize reward over time, will maximize future reward. So it's a kind of trial and error learning, and that's what reinforcement learning is all about. Now we can so there are all kinds of ways that you might fill in this box, this agent here, that's doing the reinforcement learning. But the most general way that you can really think of this, and for those of you who are familiar with Marcus Hutter's work on universal AI, I think of this as an architectural instance of Marcus Hutter's universal AI. So in the most general case, I think we can divide out our agent into a kind of compressive model or a predictive model that is able to basically a mathematical representation of how the world is going to carry on, a predictive model, and an optimal action selection component. So a component that, given this model of how the world works, is going to be able to find an action which will maximize expected reward over time. And what I'm really interested in is what's going to go into this box here, and I'm going to motivate that. So yeah. So I'm interested in particular in this modeling box here, the compressive model, the predictive model. And I'm going to motivate that by considering deep reinforcement learning. And deep reinforcement learning is what DeepMind do in their DQN agent, which was what persuaded, the demonstration of which is what persuaded Google to part with £400 million to buy them. So, so it's got to be good, right? So I'll be looking at deep reinforcement learning briefly and motivating where I want to go from deep reinforcement learning. And in particular, I'll be looking at the idea of enhancing deep reinforcement learning with a predictive model. And and I'm going to be thinking definitely quite a lot beyond what I know we can do right away. So, as I say, we were thinking about how we move towards something like human-level AI. Okay, so this is the basic architecture that we find in DeepMind's DQN. This is a deep reinforcement learning architecture. So, actually, let me just move on to the. I'll do these two slides in a different order. So just to tell you what, don't read the stuff on the right here. Just look at the Space Invaders picture, because I just want to remind you, for those or tell anybody who doesn't know, what DeepMind's DQN actually does. So basically, it learns to play retro Atari video games, and the only input that DQN has is the pixels on the screen and the reward, which is the reward signal is basically the score. And the idea is that it's a reinforcement learning agent. And it just it keeps on trying out games and playing many, many hundreds of thousands of games and trying out different actions and building up its ability to play the game better and better. And the way it does it is by using this deep reinforcement learning. So just going back to the previous slide now. So what this deep reinforcement learning architecture looks like is it looks like this. So we have as our input here to the agent the raw pixels on the screen, and this is quite a high dimensional, quite high dimensional incoming data. So what we really want to do is we really want to build some kind of model of this data that's going to better help us to predict what different actions are going to give, what rewards are going to be obtained from different actions. So the first step in this architecture is a convolutional neural network. So the kind of thing that Google and many other companies have used to learn how to label images. So we've got a convolutional neural network here, and this convolutional neural network feeds on then to a number of other layers of neurons that ultimately represent this value, this Q function. And the Q function is the function that maps from actions to their expected reward over time. So basically it's going to learn this Q function, which is going to tell it what to do, what the best actions are to carry out in any particular state, what its best guess of the actions that will maximize its reward over time are. So it's learning that through this deep neural network that starts off with a convolutional neural network and then has a few more layers, and then you have this representation of the Q function at the end. So that's what it looks like. Okay, so it's very successful in certain respects, because what they showed very nicely in the paper that came out in Nature earlier on this year, and the work has been around for quite a while too. There was earlier than that, there was an archive paper that described it a couple of years ago. Well, it's very successful at basically taking any game in the suite of retro Atari games, and it becomes pretty good at nearly all of them, or a very large collection of them. It will start completely from scratch, can learn that game, and can get to a human level ability at that game, and then in some cases it gets to a superhuman level ability, so that even the kind of like current, world Space Invaders champion is not doing any better, or is doing worse than the deep reinforcement learning agent, DQN, after it's been learning for a few days. However, when you sit and watch this thing actually, because they've released the source code, so you can actually get this thing running on a, if you happen to have some quite heavyweight GPUs, you can set this thing going on your own computer and watch it running and learning, and then you can sort of see how it performs. Now it takes a couple of days to get any good at Space Invaders, even with some quite powerful GPUs sitting there. And you can't help noticing that it's actually, in some respects, really very stupid, because it learns very, very slowly indeed. And as you watch it learning, you realize that any human player would very, very quickly realize what the kind of basic ideas of this, say we take Space Invaders, which is only one game. Of course, the important thing about it is that it's capable of learning a very large variety of games. You pretty quickly, any naive human is pretty quickly going to realize that, oh, well, you really got to get out of the way of these falling white things, and probably it's, you want to sort of send these sort of missile things up and hit these things, and you pretty quickly, are going to learn what the basic idea of the game is. But when you watch DQN running, it's been sitting there for hours and hours and hours playing these games at faster than real time, because they're whizzing around these little games, and you're sitting there thinking, well, of course, we know how it works. So you're not really expecting it to acquire that kind of understanding, because we know that it doesn't work in that kind of way. But you can't help thinking that ideally you'd like it to work in this sort of way. You're thinking, my goodness, it's stupid. Why doesn't it realize that that these things are things that are going to lose its lives? Why doesn't it just get out of the way? Because it's just behaving like a complete idiot for thousands and thousands and thousands and thousands of games before it gradually, slowly starts to get really good, and then gets better and better and better, and then becomes superhuman. So you can't help thinking that it's actually, in many ways not that bright. So one way to alleviate this kind of problem, or this kind of shortcoming, is to build in a predictive model which can look ahead at obvious threats and opportunities. And building in a predictive model, that's the start of one of those sort of things that I'm interested in when we're thinking about what are the barriers to achieving human-level artificial intelligence. That common sense thing is all about actually having a really good predictive model that has enormously wide application. So what kind of architecture might we want to, and this is the kind of thing that I've got some, the kind of thing that no doubt many labs are looking at the moment as well, not just us, but the kind of thing that I've got some students working on now is trying to augment the basic architecture of a deep reinforcement learning architecture with a predictive model. So the idea here is that we have this Q, so this is your basic reinforcement learning bit of architecture. You have your Q function here, but I'm not allowing this learned Q function to actually dictate the ultimate choice of action, but rather in parallel, I'm going to have a predictive model which is going to be looking ahead in time, and so the idea is that we want to learn this predictive model at the same time in parallel, and we're going to be constantly looking, this separate component is going to be looking a few steps ahead in time, making a guess for where things are going a few steps ahead in time. And then we're going to choose between these two distinct approaches, or these two distinct bits of the architecture are going to compete for which is going to actually decide on the final action that's performed by the architecture. And for those of you who know the field of reinforcement learning, this is a little bit like model-based reinforcement learning, but it's not quite model-based reinforcement learning. Okay. So now how do we build, now what I'm interested in now is how we build this predictive model. And so that's what I want to talk about for a bit now. And so there are lots of ways that you might try and build a really, really good predictive model. And I think this is where sort of incorporating this kind of thing into a deep reinforcement learning architecture is a very, very interesting and promising avenue for research over the next few years. So what I want to talk about now is a sort of connectionist approach to doing this, which is very much inspired by some of Geoff Hinton's most recent ideas. So, and in fact, I attended a keynote at the Royal Society in May where Geoff Hinton was talking about this notion of thought vectors that he's been sort of working on lately. And this is very much inspired by that. It's sort of, it's essentially an extrapolation of the idea he presented there. I don't know that it's actually been published in a paper yet. So that's why I have to kind of credit that keynote here. Okay, so so we're interested in building this predictive model, but now there's going to be a little bit of background for how we might do that. And I'm going to talk about some other recent bits of progress in machine learning. So first of all, the first little bit of the first little sort of achievement in machine learning I want to talk about is this approach to machine translation that Google have published, I think about 18 months ago. This is the paper by Sutskever et al. And the approach there is to use two recurrent neural networks. So recurrent neural networks basically are good at learning sequential data. So they, you present them with very large corpuses of sequential data, and then they learn to predict, given the beginnings of a sequence, then they can predict what's going to come next, basically. So what you can do is you can take two recurrent neural networks, and what you do is you take these two recurrent neural networks, one of which is an encoder, and the other is a decoder. So this one produces sentences in one language, and this one is going to take as input sentences in a different language. And you jointly train these two recurrent neural networks with pairs of sentences. So pairs of sentences that have the same meaning. So you need a very, very large corpus of good translations, of properly translated sentences, and you have these pairs, and you train jointly these two recurrent neural networks. And then, having done that, then what they showed is that this approach to machine translation, which is somewhat different from the approaches that have been around up to previously using statistical machine learning and n-grams and things, is that it's quite a successful approach to machine translation if you have a large enough corpus of data. Okay, so Geoff Hinton's sort of idea there was that what we can think of is we can think of this final hidden state in the encoder recurrent neural network, in the encoder RNN. We can think of that as a sort of as somehow encoding the meaning of this sentence. The meaning of the input sentence here is encoded in a compressed form, which is sort of language independent, because this is the form which is it's the form that you both get from translating the English sentence here, and it's also the form that enables you to produce the French sentence here. So this is a kind of compressed representation of the underlying semantics meaning of that sentence, its content. So in that lecture, he said something along these lines, that the final hidden state, which actually this is on my screen, these are in beautifully different colors. This is sort of kind of purple and this is red. So this final hidden state represents the thought that the sentence expresses. So this is what he calls thought vectors. Okay, so these thought vectors. Now what you can do is you can now train a second order recurrent neural network. So while these networks take sequences of words, which a sentence is a sequence of words, so they're learning to predict the next word in a sequence of words, or you can go all the way down to the level of letters, but let's assume it's words. So what you can do is you can translate this sort of second order recurrent neural network, which is going to learn sequences of these thought vectors. Okay, so it's taking these semantic, if you like, encodings of the semantics here, and it's going to take a sequence of these thought vectors, and it's going to thereby be able to predict what the next thought vector in a sequence is going to be. Now this is quite a profound idea, because what you can then do is you can translate these second order recurrent neural networks. You can translate them on things like, say, novels or legal documents or news reports, which are basically sequences of sentences, and you translate, you train it on these, and then you can seed it with a sentence, and it can internally rehearse potentially an entire sort of narrative, or an entire argument, or an entire chain of reasoning. So that's the kind of thing that he's got in mind. Okay, so the basic idea here is that actually I won't talk about that because I haven't quite got time, so I'm going to move on. Okay, so that was one idea I wanted to sort of start with. So this is quite a nice idea, idea of these thought vectors. But the thing about these thought vectors, the way we looked at it just now, is that they're very much rooted in human language. So one of the issues that was raised, and one of the kind of aspects of the critique of symbolic artificial intelligence, classical artificial intelligence, was the so-called symbol grounding problem. So these vectors, thought vectors in the middle there, these sort of the deepest hidden layers that are supposed to represent the content of the sentence, they're not grounded in actual interaction with the real world. So we still have what Stephen Harnad called a kind of symbol grounding problem with these thought vectors. But what we can do is we can think of an alternative way of building up a kind of something a little bit like a thought vector or a semantic vector. And so let's look at another recent piece of work by Google, and other people like Baidu have done very, very well with this as well, which is image captioning. So the idea is what you can do is you can pair a convolutional neural network. So you encode a convolutional, you use a convolutional neural network to encode an image here, and you pair that with a language generating recurrent neural network, and this produces the captions. So the idea here is that, again, you jointly train this thing with a whole load of images and a whole load of captions as your training set. You need a very, very large collection of training data, and then you can give it completely new images, and it will, quite reliably, come up with some pretty good captions, such as, dog sitting on our sofa, and and boy throwing frisbee and all that kind of thing. So, and it's the performance is very impressive, really. Although there are also some pretty dramatic fails that you can find on the internet as well. But okay, so this is another very interesting sort of bit of success in machine learning lately, and we can use this idea to get a kind of grounded thought vector, if you like, so a visually grounded thought vector. Because once again, we can think of this thing, which is the sort of deepest layer in the encoder here, we can think of that as representing the content of this image. So again, we've got something which is at the level of kind of semantics and content, but this time it's grounded in actual images rather than being just sort of part of, rather than being not grounded in language. Okay, so now we can once again translate. We can once again train a sort of second-order recurrent neural network to learn sequences of these grounded thought vectors. And once we've done that, what we've essentially got, I hope you can see, is a kind of predictive model, because we can. So let me get up the next slide. Because what we can now do with the network that we've trained is we can give it a seed image, and then we can pipe that through by generating this original thought vector. We can then pipe it through to our second order recurrent neural network, which will produce a sequence of thought vectors, and we can then pipe that back out into an image decoder. So we could imagine producing a sequence of images which basically is a kind of predictive model of how we would expect the world to unfold from this point. So that's kind of one way of building a predictive model. And in order for this to be successful, you would need an extremely large corpus of labeled images to be able to do this. And obviously there's a whole load of technical details which you'd need to go into, but I'm pretty confident that this is one approach that the big companies are taking right now to building this kind of predictive model. Okay, so now sort of the third part of this talk is I want to now revisit some of my work from the last sort of 10 years or so, and see how that kind of or how this recent progress in machine learning can be sort of folded into some of the work on cognitive architectures that I have done in the not too distant past. So what I'm interested in now, so now cast your mind back to the sort of cognitive architecture that I described, the deep reinforcement learning architecture, where you have a predictive model added to it. And now I want us to consider the possibility of using this predictive model in a more dramatic kind of way. So I motivated it earlier on through looking at something like DQN, current deep reinforcement learning agents, and thinking about how we might use a predictive model to look a little bit ahead in time, just to look a little bit ahead in time in order to hopefully make something like DQN a little bit less slow in its learning, to accelerate the learning a little bit. But now I want to look at how we might take that kind of predictive model and use it in a much more dramatic way and build it into the architecture in a much more dramatic way. And what I'm really interested in is sort of building in a kind of imagination here. So just as a kind of to show you some gratuitous pictures, right? I'm going to start by talking about Google's Deep Dream. I'm sure you've all encountered this Deep Dream on the internet, right? So you know what's going to happen next, don't you? Ta-da! so you can now the Deep Dream software is also open source now, and you can just kind of take any image and upload it, and it's not just open source, but people have got kind of web-based interface where you can just upload an image and do the Google Deep Dream thing on it. So if you do it several times on this picture of two now robots, then you get something like this. So just going back. Just going back one. So Google's Deep Dream shows how a learned model can be applied to a given image in order to produce some novelty. So basically it's taking the unsupervised learning component of a convolutional neural network, and it's then sort of exaggerating the features that the convolutional neural network sees in a given image, and sort of amplifying and exaggerating those features. So it generates a kind of novelty. But this is completely static, and what I'm interested in is imagining actions and events in time. So it's an extension of the simple kind of predictive model that just looks a little bit ahead in, say, playing Space Invaders. It just looks a little bit ahead, but we want to be able to do something a great deal more sophisticated and dramatic than that, because our intelligence is all about applying this kind of capacity to predict what's going to happen in the world and imagining whole new kinds of things. That's the sort of creativity part of it that I'm interested in. So we want something that's not just static, but is imaginative in a more dynamic kind of way that involves time. So here again we can look at recurrent neural networks. So you can take a recurrent neural network and train it on some sequential data and then sample from the distribution that it has learned. So for example, we can take a recurrent neural network, train it on a corpus of text and generate new sentences with the same statistical properties. So this is the kind of thing that we might want to do. So in fact, I took my current book, actually, The Technological Singularity, and trained a recurrent neural network on this. And this is actually a very small corpus of text because it's just one book, and you really need a larger collection of text to do this in any kind of meaningful way. But you can train it on a body of text and then get it to try to produce sentences in the style of the original corpus of text, and which have sort of the same kind of statistical properties. So in this case, it came out with a lot of nonsense, but one of the less nonsensical ones was this: the time useful into technology will be optimization parasically engineered by anagnorices. Well, I have no idea what that means, and goodness knows where it got anagnorices from. It sounds like some kind of Greek hero. But anyway, this was just, this is a spontaneously created sentence created by one of these recurrent neural networks that's been trained on the text of my book. And Andrei Karpathy from Google has got a very nice blog post where he gives you code for doing this, and he trained it on the complete works of Shakespeare and various other things, and you can see some quite amusing results by looking at that. So this has this property of being dynamic, so we're looking at sequential data, so it's not like this sort of static thing that we see in the Google's Deep Dream. But what we really are interested in the context of something like this, like a deep reinforcement learning agent, or indeed in the context of robotics, is we're interested in exploring trajectories through a sensory motor space. And that brings me to the kind of work that I was doing a little while back on cognitive architectures, and in particular on the global workspace architecture. And I'm going to talk about that in just a second. But first of all, I want to talk about thinking about this kind of predictive model that I want to build. And you should bear in mind that I'm thinking ahead somewhat here to the kind of predictive model that I would like to build in my sort of research fantasy, and don't really know quite how to build yet. The kind of thing that would, you know, have this something closer to this common sense ability to think about the consequences of actions. So this predictive model that we want to build, so it can function as a kind of internal sensory motor loop, and also it's also, you can think of it as a simulation of the external world, and it can be used for a number of different things. So this is just emphasizing the sort of potential power of this kind of predictive model. So it can be used to look ahead for threats and opportunities. So that's the sort of thing that I was talking about in the context of DQN. But it can also be used to rehearse whole sort of actions or whole plans, whole sequences of actions. It can be used to search a tree of possibilities, because what you do is when you exercise this predictive model, you don't just look ahead. Maybe you look ahead a few actions and see what the consequences of those actions would be, but maybe you have a goal in mind, in which case what you can do is you can try out, you know, a certain sequence of actions and then think, well, that one won't work, so this is, you know, internally, as it were, exercising the predictive model, and then you can sort of backtrack and think, oh, let's try an alternative possible sequence of actions. Oh, that one doesn't work, doesn't get me to a goal, so let's try a different possible sequence of actions. And this, of course, is the essence of search, of the kind of tree search you get in classical AI, and is certainly a problem that needs to be a capability that you need to endow you would need to endow a sophisticated AI with, this ability to conduct a kind of search or planning. So you can search a tree of possibilities if you've got a good enough predictive model, and you can also explore novel combinations of a behavioral repertoire, because you don't want to necessarily just look at actions that you already have often performed, but part of I can give it an entire talk on this, but part of the root of our cognitive sophistication is our ability to recombine elements of an existing repertoire in new ways to give rise to kind of whole new ways of doing things. I'm sure you guys are doing that in your everyday life at a creative company like Aldebaran all the time, right? You want to come up with new ways of doing things, ways of combining old ideas and old sort of ways of doing things into new ways. And sort of in general, this kind of predictive model is used, you can think of it as being used to think and imagine, and that's where we really want to go if we're talking about getting towards human level AI. So that brings me to, so I've been rabbiting on for quite a while, right? So I'm going to try and cover global workspace architecture in 5 minutes, yeah? Okay, so that brings me to global workspace architecture. So I spent quite a lot of the last sort of 10 years or so thinking about this cognitive architecture due to Bernard Baars. Now, Bernie Baars' motivation was that he was interested in consciousness and trying to explain the difference between conscious activity and unconscious activity in the brain. And he tried to account for this distinction using this cognitive architecture, the global workspace architecture. And the essence of this global workspace architecture is that you have a global workspace, and it's a kind of parallel architecture. So you have a large collection of parallel specialist processes, and these parallel specialist processes are all competing and perhaps cooperating, but competing for influence on this global workspace. So you can think of it as influence as them having a kind of message that they want to sort of send out. So then the winner, so this is meant to be the kind of the winning process here in this competitive dynamics. That then gets to influence or broadcast its message out to the whole cohort of parallel specialists. So that's the essence of this global workspace architecture, and in the context of consciousness, the idea is that what's going on in the specialist processes is unconscious processing, whereas what is broadcast to the whole cohort is conscious processing, and the idea there is we're interested in mapping this architecture onto the brain and empirically verifying that hypothesis. But I'm not interested in talking about consciousness here, but what I am interested in is this idea of there being a parallel architecture with a large cohort of competing processes that are competing to exercise global influence. And so a bit of work that I did and published in originally in 2006 was to show how you could combine Bernard Baars' notion of a global workspace architecture, which is cool because it can account for consciousness, perhaps, with this idea of an internally closed sensory motor loop. And an internally closed sensory motor loop is basically a predictive model, and that's what it essentially is. So the idea of this internally closed sensory motor loop is that well, we have, so you know, this looks a little bit like the original architectural picture that we had of the deep reinforcement or the reinforcement learning architecture, where you've got an agent and the agent is interacting with the world and getting input and so on. But here we have this sort of internally closed version of this outer sensory motor loop. So it enables this agent to predict the consequences of actions without actually having to carry them out. And I was interested in how you could take this kind of sensory motor loop, internal sensory motor loop, and combine it with a global workspace architecture. And so this is kind of perhaps clearer in this little picture here. So this was the architecture that I described in a 2006 paper. So there, what you have is your global workspace that broadcasts out. You can think of what it's broadcasting out as a collection of perhaps images, right? So so it might be broadcasting out an image. So the image gets broadcast to a number of competing models that are all looking to guess where to go next. So these are all sort of different predictive models, if you like, or different possible outcomes or different possible successor states to the state that I'm in now. And so these are all going to kind of compete with each other to determine what this global workspace is what state it's going to take on next. So which particular possible outcome it's actually going to sort of think about next or imagine next, if you like. And so what you would get with this is you get this sort of sequence of broadcast states. So here is an example of how so this was a kind of neural network as well, of how this network would be trained. So it would be trained to associate pairs of images. So thinking about this architecture here, I'm sorry, I'm conscious that I'm slightly rushing now and explaining something quite complex in a very short time, so I apologize. But so we have these, each of these pairs is associating sort of a current image with its expectation for what the next image is going to be. So that's what these pairs are doing. And they all have different associations. So this is the top pair, and this associates this image with this successor image, and this image with this successor image. And the second pair down has these associations, and the final pair has these associations. So for example, if the thing is presented with this particular pattern, then you can see that these two sort of predictive models predict a different successor. So one predicts the star, the other predicts these two blobs. So then in the context of this global workspace architecture, which is exploring these sort of possibilities, you then get a competition between these two sets of processes, if you like. And I'll just show you, and I'm about to sort of finish actually, and I'll have to wrap this up. I'll just show you the thing working. So you get this sequence of sort of broadcast states here. So you want to look at this thing here. So this is the sequence of associations that it has, and it's been trained to, it's been trained on pairs of images. So you see it sees one image and then a successor image, and then another image and then a successor image. And so what you saw was it just running through its expectations of where, what the sequence of images is going to be. So it's a kind of predictive model, but it's what the architecture does is it's actually sort of running this predictive model, it's exercising this predictive model and looking ahead at different kind of possibilities. Okay, so I'm conscious that I've really rushed through a whole load of ideas, and so it's been very, very hard, I think, to convey the kind of convey what I really wanted to convey. But if I'm to summarize, let me get back my slides. Well, okay. So I'd like to just kind of actually summarize at this point what I'm really interested in here. So, so cast your mind back to the original version of this deep reinforcement learning architecture that I'm looking at. So I'm interested in supplementing something like a deep reinforcement learning architecture with a predictive model. We want to build a very, very powerful predictive model, something that is capable of something like the kind of common sense that I alluded to, that can anticipate the consequences of actions in the real world. And then we want to embed this predictive model in an architecture which can imagine all kinds of possibilities, search through a whole tree of possibilities, do planning, imagine different kinds of combinations of behaviors, and integrate all of that into one single architecture. So I guess what I'm really interested in doing is building a powerful predictive model and seeing how that powerful predictive model can be most effectively employed in an architecture which uses it to sort of imagine future possibilities. So that's the essence of it. So I think I'll stop there. I feel that it's been very rushed, but I have to just finish with a plug. Finish with the plug, which is the 2 books. So I don't really recommend that you buy this one because it's obscenely expensive, but the other one less so. So I'll stop there. Thank you.